Hi, my name is Jeff Bover. I'm an associate professor in engineering, and I'm also a firefighter with Parkland County Fire Services. That's kind of how I got into some of this work. So today I'm going to be talking about extracting some fuel characteristics, some fuel data from UAV imagery or drone imagery, as well as taking a quick look at some satellite imagery, and we'll talk about some applications of this. So first, a look at the data that we have available. So there's 6 locations where we collected UAV imagery with DJI Mavic Mini last summer. The resolution of this imagery is about 2 to 3 centimeters, and it's in various locations throughout Alberta. The actual imagery is larger than the kind of plots being shown here. Here's the satellite imagery. So this is publicly available for purchase. So it's at about a resolution of 50 centimeters. That's what a tree looks like at 50 centimeters. This is what trees look like at about 2 centimeter resolution. So we'll look at trying to extract some fuel characteristics from these different types of images. So first, having a look at the UAV imagery, these are the 6 locations. Essentially, the first thing that we want to try to do is to put a box around a tree. This is tree identification, and it's the same algorithm that is used by your phone that puts a box around your face when you try to unlock your phone. Exact same algorithms. So we're pretty good at that, somewhere between 70 to 80% accuracy. So recall and precision is how machine learning algorithms are assessed on their accuracy compared to the ground truth. So 70–80% is not bad. That would improve if we had more imagery, so we only have these 6 locations, which has about 5,000 trees being used to train the algorithms. So as we have more data in the training, we would have a corresponding higher degree of accuracy. So that's for putting a box around an individual tree. We're not usually interested in exactly where every single tree is. One of the characteristics that we might be interested in would be tree density. So looking at a stand and then using the individual trees to calculate density, we're actually much more accurate in doing that because a lot of those errors cancel out. So you might have had 2 boxes around a tree, or you might have some locations where you didn't catch a tree. So those errors that affect the recall and precision of individual tree identification are sort of averaged out a little bit when we go to a larger scale and look at just the density in a larger area. So that accuracy, we're at about an R squared of 0.9. So about 90% accuracy when we're thinking about calculating the density of trees in an area. Once we've identified the tree, so put a box around the tree, we can try to classify it. So, once we put a box around a tree, what type of tree is that? Is that a coniferous tree or is that a deciduous tree? And that is very similar to your phone, put a box around your face, and then, is it my face or your face? And if it's my face, it'll unlock my phone. Same idea here. We're not trying to classify different people, we're trying to classify the trees as coniferous or deciduous. The next thing that we can do is look at structure from motion in order to get elevation data. So not only can we calculate density, we can calculate tree height for every tree that we've boxed or identified. So some of the applications, we've already discussed them. As far as fuel characteristics that we can calculate densities to a fairly high accuracy, about 90%. We can calculate tree heights reasonably well. As long as the crowns don't overlap, we can get a fairly good estimate of the tree height if we can see the ground within that box. We can get a fairly good estimate of the width of the tree, so that the size of the crown, which would essentially be the size of the box that we place around a tree. And we can also calculate mixed wood proportions, so proportion of coniferous versus proportion of deciduous. Or we could calculate not just density of trees, we could calculate density of coniferous trees. Another thing that we could do is use these techniques for monitoring. So here's the Pelican Mountain, one of the Pelican Mountain sites, and we have a location that we have not thinned. We have some locations where we have thinned, and you can imagine flying this with UAVs, identifying trees in these areas, calculating density, monitoring that over time, seeing how effective different treatments are, and using that in order to assess treatments of tree stands. Because we also have elevation, we get a fairly good 3D view of the stand. So how would we apply this? You could imagine flying over a community. So my fire chief at Parkland County allowed me to perform one of these surveys on his house. And maybe it's a little bit more clear if I remove the imagery and only show where the trees are. So this is showing the trees within 10 meters, within 30 meters, and potentially identifying them as different levels of hazard. The larger application of this would be to fly an entire community or the perimeter of a community, calculate density of trees around a community, because we're better at calculating density rather than identifying every single tree. So on a community scale, we're not necessarily interested in individual trees. We're interested in the distribution of trees around the community. And so this would be a very good application of this imagery. So that was mostly focusing on the UAV imagery, but what about the satellite imagery? So this is essentially the same type of data as the UAV data, but at a much coarser resolution, so at that 50 centimeter resolution. Same algorithms, except in this case, we're not going to be classifying the tree. We're just looking to identify the location of the trees. Now, applying this to satellite data that occurs in the winter would allow us to understand the difference between coniferous and deciduous trees. So here, we identified trees using the algorithms, the machine learning algorithms, the same ones applied to the UAV imagery. And you can see that we do a pretty good job of overall identifying the density. So here's the density calculated with manual annotations. This is sort of our ground truth, and the machine learning algorithm does a pretty good job of reproducing that density. We don't have any vertical information. We can't understand tree height. There's not enough resolution on the elevation to distinguish between ground and the tops of the trees. But we do have some promising results for understanding coniferous versus deciduous when this is applied to imagery taken in the winter. We could extend that to maybe a community rather than looking at a river. So here's Bragg Creek for interest's sake. I think it's pretty much what we would all expect. Everywhere is either high or based on this arbitrary definition of medium density. It's either high or medium density. So just to summarize, we're reasonably good at identifying trees, putting a box around trees in UAV imagery. We're really good at, once we have a box in UAV imagery, identifying it as coniferous or deciduous. We're quite good at calculating density of trees using UAV imagery. So that's that 0.9 correlation. Using satellite imagery, we're reasonably good at calculating density, where we get fairly reasonable height information and size information from trees when we can see the ground around a tree, so when the crowns don't overlap to the point where you cannot see the ground. And we can calculate distances from different values at risk. Thank you very much for your time. Again, I'm Jeff Bovair, and feel free to email me at any time with any questions about any of this work.